bias the transistor, we can use what we call collector bias, we can use base bias, and we can use emitter bias. This is a combination of a few, basically base bias and emitter bias. And this is called voltage divider bias. And this is probably the most popular way to bias a bipolar transistor. We went over this already. So this is called voltage divider bias. What is called voltage divider bias is basically this right here is nothing but a voltage divider. And what you need to do to look at this thing, you need to picture this as two circuits like this. So this right here would be, now these are generic terms. So generically in formulas, we call the two voltage divider resistors R1 and R2. And then the other two resistors we're going to call RC for the collector resistor and RE for the emitter resistor. When you get out there in the real world, these might be R15 and 32 and 68 or something like that. It's just that we have to come up with some type of numbering scheme so we can set up formulas for you, right? Understand? So when I get out in the real world, this might be R34 and this over here might be R15. But generically, we're going to call that R1 and R2 and RE and RC, right? You understand that? So now that I understand the layout of the resistors can be anything, then we can come up and we can set up formulas. So we have, of course, what we're going to do is we're going to bring our input into here. So the signal we want to amplify, we're going to bring this into here. And we're going to take our output signal right here. So we're taking our output basically across the transistor. This is where we're going to develop our output. So we've got a current valve, but we're trying to get some type of gain. Normally what we're going to look at, this guy is going to give us a voltage gain. Well, if I've got a device that gives me nothing but current, then to get voltage out of something, I've got to put a fixed resistor in series with it, right? You understand? So what the fixed resistor is, RC, is actually what's developing the output voltage. RE is in there for temperature stability. So if I come up here and clamp the base, let's say I clamp the base with this voltage divider, I clamp it at 2 volts. Then this right here, and this is clamped at 2 volts, right? You understand, by the voltage divider, which is going to set this right here at 1.3 volts. Well, what happens if I heat the transistor up? Well, if I heat the transistor up, IE would try to go up. But IE can't go up because if it did, it would change this 1.3 volts. So if this tried to drop more voltage, this right here would go down. The transistor would automatically start cutting off, right? You understand? If this current tried to go down, this voltage right here would try to go up, which would cut the transistor on more. So the transistor is locked at it, and so this guy right here is to keep the thing from going into thermal runaway. And that's the advantage of emitter bias. Emitter bias, the transistor won't go into thermal runaway. So these two guys right here are going to set the base voltage. This guy in there is going to keep it from going into thermal runaway. The output is going to be developed across RE. And now once we set that voltage, then my input signal can come in and vary that voltage. When it varies that voltage, it varies this voltage, but it's not doing it with temperature. It's doing it, if I change the base voltage, then I can change the emitter voltage. If I don't change the base voltage, then the emitter voltage can't change, right? You understand that? So it gives us the ability to bring in a signal on the base, and then we take the output off the collector. Everybody okay? This would be a typical circuit right here. What we do is we need to have the ability to bring a signal in without affecting this bias right here. So one of the things we can do with general rule, we say that capacitors block DC. And they pass AC. So what it does gives me the ability to do, if I was to come over here and put this across a signal source, this signal source basically has basically 0 DC resistance. So if I hook this up to a signal source and I didn't block that 2 volts in there, then it would drop to 0. But with that capacitor, what's it going to do? It's going to do what? It's going to do what? It's going to block the DC and allow the AC to come in. So the AC comes in, it's going to change this voltage right here, and then it's going to put a change in DC voltage right here. So when we look at this with an oscilloscope, it's going to be riding on top of DC. Because a transistor is a DC amplifier. It don't amplify AC. It's a DC amplifier. Right? You understand that? But if we have this riding on top of DC and then we have a capacitor, what's the capacitor going to do? It's going to pass the AC component and block the DC component. So that's what the capacitor does. So these have names. We refer to these as coupling capacitors. So what do? They do what? It allows the AC to couple through into a DC amplifier, and we couple it out. And we're going to look at another one. So let's see how we calculate this, guys. Well, what we're going to do is we're going to calculate this like this. So here's R1, here's R2. And right now I'm going to ignore the transistor. And then I'm going to have RC. And then I'm going to have the transistor, which is going to be one of these. And I'm going to come over here and I'm going to have RE. Y'all follow this so far? So what would that voltage, if I calculate this resistor there, what would be this voltage across R2? R2 sets the base. What would the voltage across R2 be? That's going to be the base voltage. Because notice my input signal is going to be right here. And so my input signal is connected to the emitter, but it's connected to the base, but it's common to the emitter. So we call this a common emitter amplifier. So common emitter amplifier has nothing to do with your power supply common. It's what your signal, what you're trying to amplify, what it's common to. So what would be this voltage right here, guys? If I calculate that voltage right there, what would it be? Tell me the first thing you would do. Back in DC. It's DC. It's DC. All we're doing is calculating the voltage drop across R2. If I did this in DC, hopefully you should have been able to do this, right? It's nothing but a series circuit. What would be the voltage drop across R2? Y'all working on that for me, right? What would be the voltage drop across R2? I'm showing y'all can calculate. You know everything about this thing. You can calculate everything inside this amplifier with what you should know. If you don't learn DC, you're screwed in this class too, just like you were screwed in DC. Right? You shouldn't have passed. Because all this is nothing but series circuits. So what would be the voltage drop across R2? Now what I would use the voltage divider formula, but you can calculate, you can add. So how did you do that in DC? How did you calculate the voltage drop across R2? First of all, to calculate voltage drop, what do you need to do? Using Ohm's law. What do you need to know? What two things do you need to know to calculate voltage drop? V is equal to what? Okay, I times R. So we know R, so somehow we got to figure I, right? So here we got to calculate IT. What's IT equal to? It's going to be equal to what? VCC over R2. Is that hard? Is this hard math? Okay, so calculate this voltage drop for me. Don't sit there and take your calculator and calculate this for me. What would be the voltage drop across R2? Nobody have it yet? Huh? I don't want to know the current. I want to know the voltage drop across R2. I want to know VR2. So what would be the voltage drop across R2? Anybody got it yet? What we got? 6 volts? 9.3? Let me go back and get my grade change card. Go back and change those grades in DC. So this is going to be 20 volts. 20 volts. 20. This is going to be what? 20 volts divided by 110 times 10 to the third, 110K. Okay, so it's going to be equal to this. Then I'm going to take this and I'm going to multiply it times 10K. And I come up and get 1.8 volts. I don't know where y'all coming up with y'all's answer. I did it exactly like in DC. I said, what we're going to do is we're going to treat these things like that. So that's just the way we're going to solve this. We're going to solve it like two series circuits. Okay? This is what we're going to treat it. So R1, R2, we're going to take R1, R2. So what I did is I said, okay, IT would be equal to 20 volts divided by 110K. And that gave me my current. Then I took that answer and I multiplied it by 10K to get the voltage drop. Right? And it came up and gave me what? 1.8 volts. What would be the voltage drop across R1? Now I can just use Kirchhoff's law. I don't have to do any more math. I could take that current, or I could use Kirchhoff's law. I could say, okay, I could say VR1 would be equal to 20 volts minus 1.8. Huh? Now another formula you can use is we can use what we call the voltage divider formula, which is the one I prefer to use because I don't have to solve for current. So what is the voltage divider formula? We've already used that in this class. What's the voltage divider formula? Yeah, VR2 would be equal to VR2 or R2 10K times RT, which is 100K. So I can just cancel the K out right off the bat, right? You understand? In fact, I could cancel this out right there right off the bat too. So it's 1 divided by 11. And then I'm going to take that and multiply it times 20, and that should give me the same voltage. .8 volts. So what's nice is that most of the time this is going to be a K and this is going to be a K. But if you divide right off the bat, you can strike the K out, right? You understand? Because what they're going to do, if you got a K on the top and a K on the bottom, it does what? Cancel each other out. And I got a 0 on the top. I've got a 0 on the bottom right beside the K. So that cancels each other out. That's 1/11. So that resistor will drop 1/11 of the voltage no matter what circuit you put it in. So that's what's nice about a voltage divider formula. If I was going to say, if I was to use that other formula, I say, okay, how much voltage would it drop if I changed that to 30 volts? You'd go back and you'd have to do all that math again, but it will always drop 1/11 of the voltage, always, no matter what VCC is. So that's what I like about the voltage divider formula. So we came up with 1.8 volts. Okay, and then of course we know VR1 would be equal to what? 18.2. Now what we do, now we're through with this side over here. Now I'm going to move to this side over here. Okay, wrong resistor, guys. Okay, guys, so y'all give me some idea how to do this one. Where we're going to start at. What do we know already? I don't know what the resistance of the transistor is, so that guy's out, right? But what do I know? What do I know? I know this is set at 1.8 volts. Is the emitter pointing toward minus and the base toward positive? Yes, it is. So is the base emitter forward bias? Yes, it is. How much voltage does the base emitter junction drop if it's forward bias? If it's a silicon transistor, how much does it drop? 7/10. So I know this guy right here is sitting at what? I know this guy here is sitting at 1.1 volt. I know it's 1K. I know this is 1.1 volt. So what can I calculate now? What do I know? What can I calculate? If I know the voltage across a resistor, and I know I can calculate the current. Okay, so what current would, and we call this IE, so what would IE equal to? .1 volt, 1K. What would IE be equal to? 1.1 milliamp. Okay, but what is this right here? Well, by George, that's a series circuit. What's the same in a series circuit? Current. I don't know the resistance of the transistor because it changes all the time. But by George, I know RC is a 10K, and I know that IE and IC are not equal to each other, but they're so dang close that we're using approximations anyway. Y'all understand? So what we're going to do to solve this is we're going to assume that IE and IC are equal to each other. Are they equal to each other? No. Which one's the biggest? IE. But they're so dang close, so 99.5% of IE is IC. So how much voltage does RC drop? So I'm going to say it drops 11 volts. So VRC is equal to 11 volts. What's voltage collector? What's VC going to equal to? So VC. So this is our measurement. So when I make this measurement, I'm not going to measure across RC. I'm not going to measure across R1. What I'm going to do is I'm going to look at these three measurements. I want to know what VC is equal to. I want to know what VB is equal to. And I want to know what the voltage collector to emitter is. Okay, so I want to know what VE is equal to. But we already know what VE is equal to 1.1 volts. So what's VC equal to? So what's VC equal to? So if I take my meter and put it right here, that's VC, right? What's that meter going to measure? Huh? What's it going to measure, guys? So what's that meter going to measure? Of course, we already calculated. We know VB is going to measure 1.8 volts. We know that the emitter is going to measure 1.1 volts, VC, VE. So what's VC going to measure? Huh? No. So I've got 20 volts right here. This resistor drops 11 volts. I have 20 volts right here. This resistor is dropping 11 volts. What's going to be right there? 9 volts. Whose law did we use there? Kirchhoff's law. So what's voltage collector to emitter? You say, Rich, you said we're going to measure everything to common. But voltage to collector to the emitter, so that's going to be voltage on the collector minus voltage on the emitter, and that's the way we calculate VCC. We don't have to measure VCC, we calculate it from measurements. So what's VCE going to equal to? So it's going to be 9 volts minus 1.1 volts. So what's VCE going to equal to? So are we saturated? Are we cut off? Are we in the active region? Is it equal? Is VCE equal to 20 volts? No. Is it less than 1 volt? No. We are in the active region. So now we can use this thing as an amplifier. Well, the way we calculate VC is VC is going to be equal to VCC minus VRC. That's what. Yeah, because and a lot of people want to try to subtract this for a minute, but what we're doing is we're measuring across this and the resistance. So we come up here and we said the voltage drop of VRC is 11 volts. Well, if it drops 11 volts, I have 20 volts there. If it drops 11 volts, then that leaves 9 volts sitting right here, right? You understand? Now, notice the sum of this and this equals 9 volts because we're looking across both the emitter resistor and the collector. So now we're ready to roll, guys. We calculated, we said, okay, we said IC, so we calculated IE. So IE was equal to 1.1 volt divided by 1K. So IE would be equal to 1.1 milliamp. Okay. Then we say, okay, IE and IC are equal, are practically equal to each other. So what we did is we took the 1.1 milliamp and then we multiplied it by 1K, 10K. So we said VRC would be equal to 10K times 1.1 milliamp. And this comes up and gives us 11 volts. Right, Brandon? You okay? So what laws did we use? So you just calculated an amplifier, the bias of an amplifier. And where did you learn every one of these formulas? DC. Every one of them. DC. And these are not even complicated. Even though this is a series parallel circuit, we can treat these as 2 series circuits, right? What you got to understand is we calculate this and we ignore this, and we'll talk about why in a minute. So we ignore this resistor. But what we do is we use that voltage to give us this voltage right here. Now this resistor comes into play, but this resistor is seen as a huge guy. And we'll look at why in a minute. So if this has got a beta of 100, this 1K is seen as 100K. And what's 100K in parallel with 10K? Well, it's about 9.9K. So basically we can ignore it. So this resistor right here is seen as times the beta of the circuit. And we'll look and see why. So let's bring an input signal into this thing and see what it'll do. We got to bring a very, very small input signal. So now this, as long as the base is setting at 1.8 volts, the emitter can't move from 1.1 volts. So if I heat the transistor up, it can't change, right? If I cool the transistor down, it can't change. But I can change the base voltage. If the base voltage changes, then the emitter voltage can change. So let's come over here and look at this. So what I'm going to do is I'm going to come up here and erase most of this stuff. And right now we have what? We have 1.8 volts right here. Okay. We have, what was our VC? VC was equal to 9 volts. These are the 2 important ones right here. And of course that sets 1.1 volts there. So let's bring in a real small signal on this. So I'm going to come in here and we can't bring in a signal we can't subtract from this thing. So we got 1.8 volts we can add to or subtract. We can go up, but we can't go down below 0.8 or we'd cut the transistor off. So let's say I bring in an input signal that's 1 volt peak to peak. So that'd be 500 millivolts up and 500 millivolts down. So if I subtract from the 1.8 and it comes up and gives me less than 0.7 of a volt, transistor's gonna cut off. Okay. So let's say we're going to put an AC signal into this. So here comes this AC signal. It comes in. It's 0.5 volts. It comes up here, and what are these voltages are going to do? They're going to add. So what would happen is the base voltage would go up to 2.3 volts. Everybody okay? 2.3 volts. So that means over here, what would this go to now? Somebody tell me. No, it's going to be 2.3 minus 0.7. What's 2.3 minus? Did you say 1.6? You was right. I'm sorry. 1.6 volts. Okay, so 1.6 volts. 1.6 volts. So what's going to happen? Is IE is going to go up to what? It's going to go up to 1.6 milliamp. Everybody okay? What's going to happen is this guy right here is going to go to 16 volts. My collector voltage is going to drop down to 4 volts. So this thing was setting at 9 volts, right? You understand? Now it dropped down to what? 4. Are we right? So this guy right here dropped down. Over here, 500 millivolts. Over here, it dropped down to 4 volts. So this is one characteristic of a common emitter amplifier. The input and the output are 180 degrees out of phase with each other. So when my input goes positive, the output of the amplifier is going to go down. So this drops down to here. Then I come over here and I put the 500 millivolts is going to come up here and subtract from this. So this is going to go to what? 1.3 volts. Okay, you understand? This right here is going to drop down to 1.3 volts. Oh, something's going on, guys. Oh, I'm sorry. This guy right here is going to drop down to minus 7/10. This is going to drop down to what? 0.8, right? Is that right? 1.3. I should be able to do this math in my head. 0.6 volts. So this guy here is going to drop down to 600 microamps. This guy up here is going to do what now? It's going to drop what? What's this going to go to? Now follow me so far. If I lost anybody. 600 microamps. So how many volts is this guy right here going to drop? Is this right? So 1.3 minus 0.7 is 0.6 of a volt, 600 microamps, 600 microamps. So what's this guy going to drop? So 10K, 600 microamps, how many voltages is it going to drop? Come on, guys. 10K, 600 microamps. I hadn't lost something, have I? Y'all sure are being quiet back here. So 1.3 minus 0.7 of a volt gives us 0.8. I'm sorry. 1.3 minus 0.7 gives us 6. We're going to divide that by 1,000, which is a 1K resistor, which gives us this, right? You understand? I'm going to come up here and I'm going to multiply this times 10K, which says this guy's going to drop 6 volts now, right? This guy's going to drop 6 volts. So this guy right here is going to go up to 6 volts. This is going to go up to 14 volts. So what over here, we're getting what? We're putting 1 volt peak to peak in. We're getting, what did this drop down to? This dropped down to 4 volts. Now it's gone up to 14 volts. So we got 10 volts out. But what I want you to notice on a common emitter, when this input went positive, the output started going negative. Now you have to understand this is riding on 4 volts. So what we're seeing on the output is when we turn this thing off, we're going to see this thing setting up here at 9 volts. And what we're literally doing is we're coming up here and we're superimposing this AC signal on DC. So notice it never drops down to 0. If it drops down to 0, the transistor saturates. If it goes up to 20 volts, the transistor cuts off. So right now, but look, I'm putting what into this thing? I'm putting 1 volt peak to peak in, and I'm getting 10 volts peak to peak out. Now, is the amplifier creating this power? No, it's not. We call this a power supply for some reason. The only thing the transistor is doing is manipulating that power. So transistors don't provide the power, it controls the power, right? You understand that's available for a power supply. Well, all we're doing is we're putting a sine wave in, and just by the way the thing operates, we're putting what in? We're putting 1 volt peak to peak in, we're getting what? 10 volts peak to peak out. I'm sorry. Yeah, 10 volts peak to peak out. So what would be the gain? What would be the voltage gain out of this thing? V out over V in. 10 volts peak to peak out, 1 volt peak to peak in, that's a gain of 10. It's got a voltage gain of 10. What unit is that? It has no unit. It's just a gain. What would be the power gain? Well, we don't know because we don't know what type of load this is. But if we use this as the load, now what you got to understand, we're going to have to connect this thing to something. So if I connect this to a resistor, what would you expect the gain to do? Well, the gain's going to go down because you're loading an amplifier, right? So right now we're running these things unloaded. Well, we'll figure out it's nothing but basic laws to calculate. Now the problem is if you look at this guy right here, what's the ratio between this resistor and this resistor? 10K to 1K. What's the ratio? 10. What was the gain of the amplifier? 10. Well, we can calculate the gain of the voltage gain of this amplifier just by taking this collector. We unload it by taking this collector resistor and dividing it by that emitter resistor, and that'll give us the voltage gain of the amplifier. That's how easy this is. Now, when we load it, we're going to have to consider the load. But all you do is you just take the load in this resistor right here in parallel, and we'll look at that in a minute. So this is unloaded. So unloaded, what we do is we just take this divided by this if we're not doing something pretty neat here in a minute. So see, what did we do to calculate this thing? What laws did we use to calculate? Well, those Kirchhoff's law, but notice what we got is we got a real high impedance over here. We got a real low impedance over here. This guy right here is the main guy right now. Not only is it keeping the thing from going into thermal runaway, but we're actually setting the collector current by changing that emitter. And what's so neat is this is sine times beta. Y'all understand? So this is 10K. So what would the beta of the circuit would be? Well, it'd take a lot of math. We'd have to calculate. But if you just look at this guy right here, so this guy right here, for every volt that comes over here, we get a times 100 over here, right? You understand that? Or times whatever the beta is. Which is pretty neat. So I can bring any type of AC signal in. Now, usually when we play around with amplifiers, this amplifier has what we call a bandwidth on it. If I try to put DC into this thing, this capacitor is going to block this. And these guys block DC according to a formula. You'll learn this in AC. It's 1 over 2 pi FC. So what we got to do, if I choose a real small resistor, then we get a lot. It's going to lower the lower frequency response of our amplifier. So the bigger the capacitors you use right here, the better the low end frequency response. What we do though is we got these junctions right here, and we got a conductor on this side and a conductor on that side. So these guys right here act like extremely small capacitors. So these things have what they call a cutoff frequency, which means if the frequency gets up too high, the signal will bypass the base to emitter. It'll jump right through that parasitic capacitor. So what determines the low end frequency response is what size capacitors you use, this coupling capacitor. What determines the high end frequency response is the transistor. So you set these. Now you don't want to use a real big capacitor. So this is what you're going to try to do. You're going to try to design it so it has a very small impedance or opposition at your lowest frequency. But you don't want to use a real big one because it's going to cost you a lot of money. And big capacitors are going to occupy a lot of space, right? So the bigger the capacitor is, the bigger, when we say bigger, we're not talking about physical size. We're talking about this guy right here. So a 100 microfarad capacitor would have a better a low end frequency response than a 10 microfarad, but it would still cost you a lot of money. And we don't need a frequency response in audio that's below what we can hear. About what's about the lowest frequency that we can comprehend? Anybody know? Usually around 30 hertz. Usually people round off around 15 kilohertz. Most of your amplifiers are designed around sort of that range. Telephone system, the upper end of the telephone system is like 3 kilohertz. It's very, very low. So that means using big capacitors in here, you're just wasting your money. Because you wouldn't be able to hear the difference in your ears anyway, right? So look at that. We're putting what in? We're putting 1 volt in, each peak in, we're getting 10 volts each peak out. So normally what we do to figure out the frequency response is we use a function generator. Because if y'all ever seen sound, I'll try that next class, sound is all over the place. Because not only are you changing your amplitude, you're also changing your pitch. So sound is that, y'all know what a chord is. You ever play music? What's a chord? So we have notes, and what's a chord? Most of the time we don't hear notes. Most of the time we hear chords. So what is a chord? What's it? It's a combination of notes. So if you ever learn how to play a guitar, you very seldom do you pick one finger, right? You understand? You laid off several fingers across those different strings, and you strum them all at the same time. But what you're doing is you're getting the chord. So what you do is you get all these frequencies that are combined on top of each other. So you get your bass frequency that's like this, and then you get all these other frequencies that's riding on top of that bass, and they're just all over the place. So if you ever look at audio, it's all over the place. In music's pretty straightforward because usually your drum and your bass has a constant rhythm, so you can really see the sine wave coming off your bass. But all these other frequencies, if you looked at voice, it's all over the place. But it's still AC, right? You understand? It's still AC. It's just that it's a composite signal. So what we do to look at the bandwidth is we just use a function generator, and we start off with a real low frequency until it starts passing the signal, and then we go until the signal starts dropping down. And then that way I can look at the bandwidth of what is the bandwidth, by the way? Anybody know what bandwidth is? It occurs at the half power point. What is bandwidth? It's the range of frequencies that a media can pass. So now you know, when they start talking about more bandwidth, that's what they're talking about. The range of frequencies that you have access to. So this guy has a bandwidth. We call it F1 to F2, and it occurs at what we call a half power point. So, calculate this one for me. By the way, beta is really, did we use beta in that math? So what would be the beta? Well, the beta is set by the circuit. If the transistor we're looking at could have a beta anywhere between, 30 to over 300. Well, what we do with this is we set the beta of the transistor. So we can set it, but it's got to be somewhere between its minimum beta and maximum beta. And once we set that beta with the bias, then the beta is, and we use voltage divided bias, and the beta is set. It cannot change, right? You understand? Because of that emitter resistor. So calculate this for me. So what do we want to know about this thing? What do we need to know? What are we going to calculate? We're going to calculate dB, right? Once we calculate dB, we need to calculate dE. Once we calculate dE, we need to calculate IE. Once we calculate IE, we're going to calculate VC. Once we calculate DC, then we need to be able to calculate VCE. This don't look like it did. Anybody got VB yet? What we got for VB? VB, guys. It's been less than 30 seconds to do that. VB. What y'all got for VB? So 10 divided by 32 times 30. So what do we got for VB? Come on, guys. What do we got for VB? What's that? 9.4 votes. So what do we got for VE? What do we got for IE? It's 1K, guys. Yeah, 8.7. What I like about 1K is that it's 1 milliamp per vote. So what we have for VC? This would be a waste of time, amplifier. We're just doing this for math. Because this guy here would only have a gain. This guy here would have no gain at all. He'd have a gain of 1. So what's VEC? You got something for VC yet, Randy? 8.7. You got anything for VC, Corinne? You got anything for VC, Courtney? Scott? Charles? So VRC, which we're not using, VRC would be equal to, is everybody okay so far? 8.7 milliamps, right? 9.4 volts. Are you okay? Everybody okay there? Y'all need to go back and look at any of those calculations.
Yeah.
VB is set by these two resistors right here. So I'm going to use the voltage divider formula. It's set across R2. So when we calculate VB, VB is all these measurements are made relative to common. So when I look at that meter, it's across R2. So if I can calculate R2, then I've calculated VB. So if I use the voltage divider formula, I'm going to say VR2 would be equal to the resistor I want to find the voltage drop across, divided by the resistor by the total resistance, which would be 32K. And what's going to happen right off the bat? The K is going to cancel. And then I'm going to multiply that times 30 volts. When I do that formula, it comes up and gives me 9.4 volts. or 9.37 or something like that. Yeah, what you do when you take Rx over RT is that gives you the ratio that resistor drops in that circuit. And what's nice about using the voltage divider formula is if I was to come up here and make that 40 volts, the ratio would still be the same, right? You understand that? So what you learned in DC, they should have taught. Did they teach all the voltage divider formula in DC? They should have. Okay, so now we know that, then what I do is I say VRE, which is voltage drop across RE is going to be equal to VB minus whatever transistor it is. And these are silicon transistors. And that's where we came up when we got the 8.7 volts. Then we know that IE is going to be equal to 8.7 divided by 1K. And that gives me the 8.7 milliamps. We should give you the voltage drop across RC because it's a series circuit. Current's the same. This guy's 1K. It drops 8.7 volts. So VRC is going to be 8.7 volts. But we don't measure VRC. We measure VC. So what will VC be? So what would VC be? Huh? It's not going to equal VE. It can't equal IE. Guys, this is what I want you to see. I mean, if you work these circuits all the time in DC. So VC, where do I measure VC at? So I'm going to measure VC. I'm going to come up here and put my meter in here. So the way I measure VC is I take my red lead and I put it right here. I'm sorry, I put it right here. And I take my black lead and I hook it up to common. So the only difference between VCC and VC is the voltage drop across RC. That's the only difference. For some people want to throw this in, but I'm measuring all the way across the transistor. I'm measuring across two resistors. Huh? What's VC? Huh? So what's VC? If this resistor right here drops 8.7 volts, then what's VC equal to? It drops 8.7 volts. I'm measuring after that voltage drop, so what's VC going to equal to? Huh? 21.3. I remember all those circuits in DC, those series parallel circuits. They'd come over here and they'd put resistors right there, and they'd come over here and do this and put resistors right there. They'd come over and put resistors right there, resistors right here. That was the series parallel circuits that you had to work in DC. These guys, this guy right here is nothing compared to that. Y'all remember those circuits? When I took DC, the guy liked to draw them in triangles and rectangles, and he'd put triangles and rectangles all through there in his circuit. He would try to confuse when I took DC. But these are just two series circuits. It's a series parallel circuit, but all we do is treat them two series circuits separate. Very simple series parallel circuit. So voltage collector to emitter is now, this right here is going to be this voltage that I measure between here and here. But I don't have to measure it because I know everything I need to know. I know my collector voltage, and this tells me the formula. So my voltage collector to emitter is going to be the voltage on the collector minus the voltage on the emitter. So my voltage collector to emitter, CE, is going to be equal to 21.3 volts minus 8.7 volts. And this amplifier here is going to give us a gain of 1, so it's not even worth our time. This is a good circuit just to get an understanding on how to calculate these dBs. This would be a junk amplifier, because if I don't get a gain out of it, it's worth nothing, right? We could get a current gain out of this, depending on the load, but one of the big advantages of a common emitter is we get both a current and a voltage gain out of it. So what would my VCE be? 21.3 minus 8.7, what's that? So we're operating in the active region. But we throw that transistor in there and everybody gets scared. But it's nothing but what you learned in DC. It's nothing except the gain. So what would be the gain of this? This guy here wouldn't have a voltage gain. It has a gain of 1. So if I put 1 volt peak to peak in, I get 1 volt peak to peak out. We don't know the current gain because we don't know what load we're going to feed this in. So let's calculate this one. Oh, we've already calculated this one. Ah, dang it. We've already calculated this one. That was the same one we calculated before, guys. Come on, come on, come on, come on, come on, come on, come on. Good custody. We're going to do this lab next week. So let's talk about one more thing. And then I'm going to give you all a worksheet. That'll be due next class. So why did we calculate that one? This was 1.8 volts. This was 1.1 volt. This was 9 volts, right? And then it had a gain of 10. So right now we can calculate the voltage gain by taking RC divided by RE. We're going to change this. This is actually R out. So we'll look at that in a minute. Well, we probably won't have time to do that tonight. And then, so right now this is going to be 10 divided by 1. So this gives us a gain of 10. That has no units. Everybody follow me so far? Everybody okay? We call these capacitors right here have names. What do we call these capacitors? We call these coupling capacitors, right? Because they allow us to couple an AC signal into a DC circuit and couple an AC signal out. Everybody follow this so far? Now the problem is this guy here only has gain of 10. the input impedance is pretty high. So what my input signal sees is it comes flying in right here, and then it splits here and splits here, and then it comes over here and splits this, and then this is what my input signal sees, which is a lot of impedance. So mathematically, if we wanted to calculate the input resistance, then Rn would be equal to R1 in parallel with R2 in parallel with Re times beta, the beta of the circuit. So it'd be a pretty, it's not really involved that much. So Rn would be equal to 1 over 10K plus 1 over 100K plus 1 over, let's use a beta of 100, plus 1 over 100K. So the input impedance would be around 9K. And that would be what we call the input. So that's what the signal would say. The output resistance of the circuit would be this guy, and then we're going to connect this to a load. So right now, what we'll use is just the resistor. So if we call this R the L, then my output is developed right there. Then R out or Z out would be equal to RC in parallel with RL, R the load. That would give me, so it would be useless of having an amplifier if you didn't connect it to something, right? Y'all understand? But the problem is, if I connect a load to the amplifier, then my gain has got to go down because we're loading the amplifier, right? You understand? So the actual formula for calculating gain would be equal to Re over R out, or Z out. So what you'd have to do is you'd have to know the size of this, and you'd have to know the size, you'd have to know this. This is pretty easy. Sometimes this is not easy, because a lot of times what we do is we have one amplifier feeding another amplifier. So if this has a gain of 10, if I took the gain of this, which has a gain of 10, and I fed it into the same amplifier, then we would have a total gain of 100, right? You understand that? So for me to calculate the gain, I would have to calculate the input impedance of this amplifier to calculate the gain. So it gets a little complicated on calculating all the gains. And we're not going to have you do that in this class right now. But what we do need to do is understand what we can do to get more gain out of this thing. Let's say I wanted more gain. Well, what could I do to get more gain? Anybody got any ideas? Can't increase the voltage because this guy here has a gain of 2. I mean, I could put 30 volts up there on VCC and it would still have a gain of 10. VCC has nothing to do with the gain. All we got to do is just make sure we don't exceed the range. So if my input voltage cut the transistor all the way on, then what we'd end up with is it would be clipped on the output like that. If I turn this thing off and then I kept putting input signals, then what would happen is the tops would be clipped. So if it's clipped on the top, we call that cutoff distortion. If it clips on the bottom, it's saturation distortion. But what we've done is we've added distortion to our signal, right? You understand? So what would I do to increase the gain? Well, what's the gain equal to? Well, we said the gain, AV, is equal to R. Right now it's equal to R out over Re. So one thing I could do is I could change the ratio of those resistors. I could make RC bigger. If I make RC bigger, I get a bigger gain, but it would cut off or saturate faster, right? Because it would drop more voltage. Or I could make Re smaller. If I make Re smaller, we would get more gain. But what we want to do is we want to keep all these formulas that we got, and we want to add more gain to the transistor. The problem is my input signal has to come in, and it's got to go through that resistor right there. So that guy right there is what's limiting the gain. If I can make that guy really small, then I can get extremely good gain. But the problem, if I make it extremely small, my bias current goes way up, right? You understand? And the whole amplifier gets out of whack. So what we would like to do is come up with some type of method where the input signal does not have to go through my emitter resistor. And what does the capacitors do? What does the capacitor do? Well, it blocks DC and passes AC. So what I can do is I can come over and do this. I can add a capacitor right there. What are these capacitors called? This capacitor right here is called a bypass capacitor. Now what happens is my AC signal comes flying in right now. If I choose these capacitors right, my AC signal comes in, it goes that way, it goes this way, it comes over here, and does what? Now don't change your bias. It don't change your math as far as calculating your biases at all. The thing won't go into thermal runaway. But basically it causes the AC signal to bypass that emitter resistor. Now what are you saying? It says it looks like it's a short circuit, but it's not. What we do is we have a junction right here. And this junction has a resistance. It's got an R value. And we looked at that, so when we did our characteristic curve, we came over here and we noticed that thing was at a slant. Well, what causes it slant? It's the R of the actual junction itself, right? You understand? So when we say a diode is forward biased, we say it acts like a closed switch. That's not true. It's a closed switch with a little bit of resistance in it. Now what we do is we call this resistance right here, we call it RE. I call it RE prime. So to calculate the gain, we need to be able to get an approximation of what we call RE prime. Now we do this with calculus, and I can give the formula sheet is up there. But they go through they use Kelvin, they use temperature, and all the dynamic resistance of a junction. But no matter what you do, this always roughly works out to be equal to approximately 25 millivolts over IE. So what would this resistance be? So what was our IE? We had 1.1 volt there, right? We had 1.8 volts there. We had 1.1 volt right there. So my IE was 1.1 milliamp, 1.1 milliamp. So I'd take 25 milli over 1.1 milliamp, and that would be the approximate resistance of the PN junction. What does it give me? $25 millivolts over 1.1 millivolts. About 22 ohms or 23 ohms. Huh? Okay, so 23 ohms. So my AC does not see this resistor anymore. This is what my AC sees. It sees that 23 ohms. So now my gain is going to be 10K divided by 23 ohms. And what would the gain to be now? So look what the gain of this amplifier went up to. So it went up to 434. Now, it seems like this would be the route we ought to go, but what happened is we just lowered our input impedance a lot. So that means my signal would have to provide a lot more current to get this gain. So anytime we bypass the emitter resistor, the input impedance or the input resistance goes down. If my input resistance goes down, then my signal source is going to have to provide more current to get this 434 gain, right? You understand? So we won't use a bypass on something that's got a high. So did we talk about impedance matching in this class? Did we? Yeah. So what we're doing is we're going to look at the characteristics of these different amplifiers, and we're going to learn every amplifier has a different impedance, a different characteristic. And basically, it deals with what input impedance it has relative to its output. So common emitter amplifiers have a relatively low input impedance and a relatively high output impedance, which means we don't want to match something that's got a high input impedance to something that's got a high impedance to a low impedance, right? You understand? So what we're going to do is we're going to choose what type of amplifier we're going to use depending on what type of impedance is going to come from the signal source and what type of impedance is going to go to the load. So if I wouldn't hook up a common emitter to a speaker. I could, but it's going to be very poor performing because why? Because it's got a high input impedance. I'm sorry, it's got a high output impedance. And what's the impedance of a speaker? What's the typical impedance of a car speaker? Anybody know? 4 ohms, about 4 ohms. A typical impedance of a home speaker is about 8 ohms. This guy here's got an output impedance of up into K ohms, so that means I could drive a speaker with this, but I'd get very poor what? I'd get a very poor power transfer. It would load my amplifier around a lot. So to drive a speaker, I need an amplifier that's got a low output impedance, right? You understand? Which would be a common collector. So that's what we're saying. So you choose an amplifier depending on how much load does the signal have to provide and how much impedance that we feed this thing into. So one of the characteristics of a common emitter amplifier is it's got a fairly high input impedance. A fairly low input impedance and a fairly high output impedance. So it's a good amplifier to get middle stage gain in, but it's a very poor amplifier to get a lot of power gain out of, right? And we can get a lot of power. So a common emitter is a really good amplifier. This is probably the most widely used amplifier out there because we can get both a current and a voltage gain out of this. The current gain would depend on what we connect the load to. And then, of course, the voltage gain we've seen out of this. So I'm going to go ahead and give y'all a worksheet, and we'll turn this in when. All we're going to do, line up on there and take when I get it printed off. Make sure y'all give me y'all's pets back, right? Put them up there on my desk.
Ain't no ad, no nothing. Yeah.